Hello, do you hear me?
Hello. Hello.
Yes, Anupam, can you hear me?
Yes, I can hear you. Do you hear me?
Yes. Anupam, can you hear me from the classroom?
Hello. 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 No, we can. Hello.
Hello?
Hello, Alexey, can you hear me?
Yes, I can hear you.
Hello,
I can
Alexey,
see
can you
you.
hear me?
Yes, I can hear you.
We need some more volume. Hello, can you hear me?
Yes, I can.
Okay, that sounds better. Camera is on?
Can I try sharing my screen now?
Yes. So can you see the audience here?
I'll see the top of your head and my face on the screen.
Top of my hair, okay.
Okay, now I see you better. Thanks for showing the audience.
Okay, now we can see, of course. So maybe we can start now. So as you know, all of us, all of you, that we are celebrating the International Year of Quantum. And we have a series of colloquia in that. And today's talk is the 11th of the series. And the speaker is Professor Alexey Ustinov. So let me introduce the speaker. Mr. Alexey Ustinov is a professor of experimental physics at the Karlsruhe Institute of Technology in Germany. He was associate professor of experimental condensed matter physics at the University of Erlangen, Nuremberg between 1996 and 2008. And before that, between 1989 and 1996, he worked at various universities and research laboratories in Germany, Denmark, and Italy. And he received a PhD degree in physics and mathematics in 1987 and a Doctor of Science degree in 1995 from the Institute of Solid State Physics of the Russian Academy of Sciences. He also served as a member of the Scientific Advisory Board of the Russian Quantum Center and led the Laboratory for Superconducting Quantum Technologies at the National University of Science and Technology in Moscow. He received many awards, and out of that, I think one is Humboldt Fellowship, of course, and the Stefanos Nevatikos International Award of Research in Nonlinear Science, Mega Grant of Russian Federation, 2011, Google Faculty Award, 2017, ERC Advanced Grant in 2022. Professor Ustinov has published over 300 research papers in peer-reviewed journals, supervised over 30 PhD dissertations, and numerous undergraduate students. Major scientific contributions of Professor Ustinov are in the areas of low-temperature physics, superconductivity, Josephson junctions and arrays, nonlinear dynamics, solitons, and superconducting quantum circuits. And the title of his today's talk is Identifying Material Defects in Quantum Circuits. Professor Ustinov.
Thank you for your kind introduction. Let me share my screen.
Sure.
So do you see the screen?
Yeah, you see your screen.
Okay, so let's get started. I think I suggested several different topics, and this topic seemed to be kind of attracting more the audience than the others. So I'm going to speak today about microscopic defects which occur in macroscopic circuits. So defects are of the size of, let's say, a nanometer or smaller than nanometer, and circuits actually are of the size of millimeters. So really two different scales. This picture is a teaser, which I'll explain a bit later. Let me say a few words where I'm coming from. So I'm coming from Karlsruhe Institute of Technology, which is located, as this map at the bottom left shows, in the southern part of Germany, very close to French border. And the town is about 300 years old, and it has a university which is also over 200 years old. Actually, the university is associated with the name Hertz because here Heinrich Hertz was making his experiments in detecting electromagnetic waves. Now, the university, as a technical university, existed for a long time, since 1825. So this year is special, as you understand. And there was a big change, actually, starting from 2009, because the university was merged with the national lab, which was a lab of the Helmholtz Association. Actually, it's called Research Center Karlsruhe. So now altogether it's called Karlsruhe Institute of Technology, which does both educational and research activities. And to my knowledge, is actually the biggest organization of this kind in Europe, with an annual turnaround, annual budget over €1 billion. So I'm representing my group, which is a couple of young people, postdocs, students, like PhD students and master students, and permanent employees, very few of them. And we are working on various aspects of superconducting quantum circuits associated with superconducting qubits for quantum computing. Our more recent work actually is an attempt to bring the frequencies of those qubits from gigahertz range to 100 gigahertz range, going to the millimeter waves. That's a challenging project which is funded by European Research Council, ERC. We have been working on the various things associated with superconducting devices like flux qubits, stack junctions. Currently, we work on very compact inductors for quantum circuits, quantum phase leaps, and beyond. So today I'm speaking about the topic which is one of the listed here, which is two-level defects in qubits. So that's the same picture which you have seen in the very beginning. So let's get started. Well, the superconducting qubit, or any qubit, is a two-level quantum system which contains two eigenstates of energy for the system. And without going into details of the hardware, which I will do a little later, just to explain what we are talking about here, we are talking about the quality of these quantum systems. So we are talking about the coherence, which actually is limited by, generally speaking, two major processes characterized by times T1 and T2. So the characteristic time of T1 is basically the relaxation due to the interaction with the environment. So if you excite the system from ground state to excited state, then it relaxes by emitting a photon to the environment. This photon for superconducting qubits is in the microelectron volt energy range, which corresponds to a frequency of few gigahertz. Now, the environment also acts back on these devices by applying random fields, which you cannot control. And these random fields lead to the fluctuation of the energy level separation, which primarily leads to the dephasing. So this leads to the kind of fluctuations of the energy level separation, and that means that by controlling this device with specific frequency, you will get some uncontrolled dephasing, change of the phase of the quantum state, which can be formed between those two states if you, for example, make a superposition of those. And this field worldwide actually opened up over 20, actually about 25 years ago, when people were first time able to observe macroscopic quantum coherence. So that actually macroscopic circuits can show quantum properties, which are characterized also by this type of metrics as T1 and T2. And obviously, if you want to do a quantum computing which utilizes the properties of two-level systems, then you would like to have as long as possible coherence times, T1 and T2. And these coherence times, they've been going up and up over many years, reaching the range of, let's say, starting from nanoseconds up to tens and hundreds of microseconds. In the beginning, the progress was almost exponential over the first 15 years, but then the progress was very strongly slowed down. And currently, the coherence times of the superconducting devices are in the range of, let's say, a fraction of millisecond or a millisecond. So the primary source of these limitations of the coherence times has been identified over those years, and this source are microscopic defects which occur in the material of superconducting electrodes of circuits. So that's basically a subject which I'm going to focus today. We would like to study actually the physical properties of those defects and actually understand what they are. So the defects are unknown origin. So what we know about those defects, they occur in disordered materials. They occur on the they can occur on the tunnel barrier of a Josephson junction, which will be basically inside the superconducting qubit. They can also occur on the surfaces of superconducting electrodes, which when circuit is fabricated, the electrodes are in contact with air, and they get oxidized, of course. And then there could be oxides, some disordered fractions of the materials, could be adsorbates on the surface. This could be residuals of the photoresist. And they can be also defects in the junction. So typical material for superconducting quantum circuits is aluminum. And when you make a Josephson junction, you simply oxidize metallic aluminum in a vacuum chamber, forming a few nanometer thick oxide layer. This oxide layer is disordered typically, and then depositing the top aluminum actually does not make it crystalline anyway. So there is a disorder in the oxide barrier, and this disorder can be, for example, due to some tunneling defects, which could be individual atoms in the resource structures or groups of atoms. This could be tunneling bonds, this could be spins, this could be many different type of defects have been proposed. And these defects, they occurred actually first to be speculated back in the beginning of 70s. About that time, people started looking into disordered dielectrics at glasses. And the glasses have shown very significant deviation in their properties at low temperatures. And these properties were basically showing that there are additional degrees of freedom which contribute to storing the energy in these materials. For example, specific heat was much larger, by orders of magnitude larger than in crystalline materials. And simultaneously, there was a model which is now being called standard tunneling model, explaining two-level systems, TLS. This model was proposed simultaneously by Phillips and P.W. Anderson with colleagues, stating basically that in a disordered material, you may have an object which could be, as I said already, a single atom or a group of atoms tunneling between two stable locations, forming effectively a system in a double well potential. As you know, quantum mechanically, this double well potential appears, for example, in textbooks like Feynman textbook about physics. As an example, is ammonium molecule, which is an example of spin one-half system in magnetic field. So if you have spin one-half system, then the energy spin up and spin down is the same at zero field. However, if you apply the field, then of course this degeneracy is lifted, and basically you would have two different states of different energy. However, quantum mechanically, the lowest two energy states will be superposition of the spin up and spin down states. And therefore, of course, that analogy also exists here. The energy scale of an ion of the lattice in a solid is in the electron volt range. However, the phenomena which were observed by experimentalists that time, looking at glasses, they were in the micro electron volt range. So they were actually observed at temperatures well below 1 Kelvin, which would correspond to the characteristic photon frequency of about 20 gigahertz. So it was well below 20 gigahertz. That means that actually the barrier which you have is very narrow, but very could be also very high. And the only process which can happen is such as steep wells rising on both sides of this barrier could be tunneling. So the Hamiltonian of the system, as shown here, is written as a sum of the two terms. One of them is basically corresponding to the situation in symmetric well, and is characterized by the tunneling splitting delta. And the second term is the corresponding to the asymmetry, which is due to the asymmetry of the well. And it has been already realized a long time ago, studying losses, that you can influence this asymmetry by either applying electric field or applying strain to the system. So you produce a tiny deformation of this lattice, either mechanically or by applying electric field, and therefore you could change the symmetry of the two. So you could look at these defects as a kind of microscopic dipole, which interacts with strain and electric field. And obviously, this kind of defect will be coupling to qubits and phonons and all kind of excitations in superconductors, including also quasi-particles and other two-level systems. So in this talk, I will distinguish between different types of defects. So one type, which I will like to call coherent two-level systems. This will be two-level systems which will have their coherence times, which means they let's say T1 of transition between the lowest energy state and the first excited state, basically shown by these dashed lines in the sketch up left. So I will call them coherent TLS if they basically form quantum states which live longer than the tunneling rate. And then I will call also the other types of TLS which are also present in the material. I will call them fluctuator. Those will have the lifetime much shorter than the gap, and therefore they will be always incoherent. So in this case, you would not expect any coherent coupling to, let's say, quantum circuits, which we study in experiments. So these defects are not only unique to superconducting circuits or disordered materials. They are actually found in a variety of systems, in nanomechanical systems, in optical cavities, ranging from laser mirrors, and also they are limiting the accuracy of LIGO interferometer used for gravitational wave detection, where they occur on the surface of amorphous titanium oxide on the surface of the mirror. They occur also in other types of quantum computing systems, like entrapped ions. They can be on the surface of the electrodes. They can occur also on the surface of semiconductor spin qubits. And in many other examples exist. They even occur in the accelerator cavities, where they limit the quality factors of the cavities. But of course, at large power, they would be saturated, but nevertheless, they will limit the coherence by giving away the energy through the emission of phonons in the material. So all these examples are versatile, but here we focus on superconducting devices. So this is a picture which is a kind of very quick introduction into superconducting qubits. So superconducting qubit is basically a Josephson junction, or if you want to control the energy, Josephson energy of this junction by magnetic flux, you can use a double junction forming a loop, which is called squid. And then applying a flux, you could change the Josephson energy of this device. And this device is characterized by two energy scales. One is the, as I mentioned already, Josephson energy. The other one is the capacitive energy, because every Josephson junction is a capacitor. Now, typically the device is in the range of, let's say, a few hundreds of nanometers times about same size. And the tunnel bearer is about 1-2 nanometers. However, in order to bring this device in a convenient range so that the energy levels do not fluctuate very strongly due to the parasitic charges or charge noise on the chip, people learned to make those devices shunted by a capacitor, by external capacitor. And if you shunt this by the capacitor, then you make the first term in the Hamiltonian significantly smaller, and then the fluctuations of the straight charge lead to do not lead to the energy level fluctuations in the qubit, and therefore the coherence is enhanced. These devices are called transmons. For historic reason, the name is a bit strange. But anyway, these transmons are weakly anharmonic systems where the potential is cosine-like dependence of the energy on the flux. And then typically there will be less than 10 energy levels, eigenstates in the potential well. And since the potential is cosine, there will be anharmonicity. So the ground state transition to the first excited state will be slightly larger in frequency than this transition from the first excited to second excited. So this anharmonicity is only a few percent typically. And if you just operate at the lowest energy transition, then you could sort of approximate this as a two-level system. And this device is being used in all quantum computers nowadays. Google, IBM, Rigetti, or others, they use this type of devices. Now, it turns out that actually these devices already in the when they appeared even before the transmodels were invented in the phase qubits at that time, people found that the energy spectrum of the device is being non-continuous. There are some frequencies which show avoided level crossings with some defects. And these avoided level crossings can be of different scales. It could be really comparable to, let's say, detectable frequencies, like in the range of few megahertz, but could be simply some frequency where the coherence is decreased. So this dependence of the spectral properties of these devices in microwave range led to a variety of models predicting those two-level defects. And as I mentioned, they could be really of different origins. Some of these theoretical proposals, which are listed here on the right, have been checked, some of them not. There is a very rigorous review of this topic written by my close collaborator, Jürgen Lissenfeld, and co-authors, and published in Reports on Progress of Physics. So the defects, they occur not only the tunnel barrier of the junction, which you see here on the top, as an example of the layer between two superconducting materials, but they can also occur on the surface of superconducting material. Let's say due to adsorbates, they can be just atomic tunneling systems in the oxide on the surface. There can be residuals of the photoresist, some contamination. There have been also proposals this could be defects due to the trapped quasi-particles, like you have a small region of the reduced gap on the surface, and quasi-particle can come there and not being able to pair with another electron, this excitation sort of would stay there for a long time. So this variety of models have been used also to, some of them have been used to explain properties of glasses, but in glasses, no one ever have seen a single two-level systems because people were always studying the ensembles of the systems. And it turns out actually with the invention of superconducting qubits, we could see individual two-level systems. And this is really unique because we could also study, we could use a qubit as a kind of microscope, as a device, as a spectrometer to explore properties of microelectron volt range defects in solids, defects which occur in dielectrics and disordered material on the surfaces. So if you measure the lifetime of the qubit excited state as a function of frequency, you'll find a lot of bumps, and that's what you see here on the top on the plot on the left. The bumps are there due to the coupling to the microscopic defects. And this very bumpy frequency dependence, the left-hand dependence on the frequency, leads to a large spread of parameters of artificial two-level systems fabricated in superconducting processors. And here you see on the left some data for Google device some years ago, more recent data for IBM device with 127 qubits. You see such a large spread of relaxation time for the qubits fabricated nominally identically on the same substrate. Now, if you measure the T1 time of the device, specific device, you also find that it's not really stable. It fluctuates on the time scale of minutes to hours and even days. These fluctuations are actually of the order of the relaxation time itself. And one of the ideas to explain, actually most probable idea, which has been proposed initially, I think by Google and then followed up by us and also people at Chalmers University about 6-7 years ago, the idea is the following. So if you have a two-level system which is coupled coherently to your qubit and limits the coherence of the qubit, there can be also another two-level system coupled to the first one. And if this another two-level system is incoherent one, which we will call thermal fluctuator, then the random change of this phase of the state in the double well potential of this fluctuator may be coupled either by strain or by electric field to a coherent defect, which in turn will slightly change the frequency. And this changing frequency of this defect will unavoidably influence the coherence time and also relaxation time of a qubit, which is parked at the nearby frequency. So basically, this interaction of the two-level defects, one of them incoherent, the other one coherent, explains these fluctuations of the coherence time of superconducting devices, and also it actually recognizes the major problem because you need to recalibrate superconducting processors very frequently, and this takes time a lot to do this. Actually, this makes the whole calculation rather inefficient. So going back to studying these defects, so what we proposed initially around 2012, and this was our first paper when we observed the very individual TLS. This was a science paper 2012. What we did, we proposed to apply strain to our device. So what we do, we take our chip, which you see here at the bottom left here, the chip containing a quantum circuit. And then we use a piezo actuator to deform the chip, so to apply some tension between the clamps. And then we introduce some little bending of this silicon chip. We could also done it with sapphire, but silicon works is easier. So and then this bending introduces a variation of the frequency, only sorry, not the frequency of the flatness by the scale of a micrometer. But this leads to the deformation, which will be seen on the atomic scale in the range of 10 to minus 7 or so. And in this case, we basically are able to introduce some strain, and the strain may lead to the change of the electric properties of the circuit. And that's what we observe. So we observe the following. So you see now the plot which you have seen horizontally shown on the previous slide. On the right, you see this very right plot is the frequency dependence of the qubit loss rate. And the resonances indicate coupling to the individual two-level systems. Now, on the plot to the left of it, you see on the gray scale, again, the qubit loss rate. So white spots are low loss and black spots are high loss as a function of frequency, the vertical axis, and strain. And what you see is actually very clearly, you see a lot of traces there. Those traces are individual two-level systems which vary their frequency independence on strain according to the textbook formula shown on the plot to the left above. So the generic formula for the energy level separation for a two double well potential is the square root of delta square plus epsilon square, where delta is a splitting in the symmetric well and epsilon is the symmetry parameter of the potential. And you see all those curves, they resemble very much these hyperbolas, which could be flat or steep, well seen or not well seen, but all of them are really of this generic shape. Some of these hyperbolas, they end below the bottom of this plot because we only are able here with this qubit of particular frequency to scan the frequency range in the range of about 20%. So some of them have frequencies well below that. But clearly, this type of plot is direct confirmation that these defects are two-level systems. They have really textbook dependence of their frequency on a symmetry parameter. They have a random distribution of their gaps. And they also have different strengths of coupling to the qubit. So over years, we have done a lot of studies of these defects, measuring their coherence rates as a function of frequency, measuring the interaction between them, and a lot of different things. I will show some of the citations here. Now, to give you an example of one of the measurements, this is, for example, the measurements of one of the qubits back like 10 years ago already. And these plots actually resemble very much some old-fashioned plots which particle physicists were obtaining in the cloud chamber using the old-fashioned detection technique. So really, if you take better and better qubit, you have here better and better frequency resolution. And in this case, you see more and more defects. So actually, the number of defects here is only limited by the quality of your qubit. Better qubits is more defects, but of course suffers less because it's better qubit than bad qubits. So if you're interested in some details, we could discuss it later. So some of these lines are not a single lines, but double lines, but this is just due to the artifact of our detection technique. So what we basically do, we excite the qubit by a pulse, which is fixed length. And then depending on the strength of coupling, you can, what we do, we park the qubit first far away from the defect. Then we excite the qubit to the excited state. We bring it to the frequency of defect, and then we measure the result of the qubit population after we detune the qubit away from the defect. So we can have strongly coupled defects. In this case, during the time at the defect, the excitation can perform several swap exchange oscillations between the artificial and the natural two-level system, between the qubit, a superconducting qubit, and the artificial and the microscopic defect in the circuit. So for strongly coupled defects, we observe those shades. But you also see really interestingly here some of these lines, they are interrupted in a random way. This is like telegraph switching due to the presence of the incoherent defects next to the coherent one. Some of these defects also show the interaction with each other, which I'm not going to discuss today. So really a variety of different very interesting properties. So here are some references from our group over the years where we have been studying those defects and where we have actually seen a lot of interesting physics. Actually, this discovery opened door to studying microscopic defects using superconducting quantum circuits and learn a lot of interesting facts and experimental artifacts about their properties. We have learned how to excite defects directly. For example, we could shine microwave frequency at the frequency of the defect and then use the qubit to read out the defect. We could change the frequency of the defect by strain and measure the T1 and T2 time of the defects as a function of frequency. And well, clearly is a two-level system, so the largest dephasing time is at the bottom of this hyperbola at the lowest frequency, where T1 is almost half of the T2. If you go away, then of course fluctuations in the environment lead to the dominant T1 being the longest one and T2 being the shorter one. So a lot of these studies have been performed. Now, what is more recent, okay, it's also already like about 5-6 years we are doing that. We are not only able to control these defects by strain, but we also can control them by electric field. So here you see the setting on the right, where we have the setup I already explained, the qubit chip clamped between two supporting bars, metallic supporting bars, and then by applying a voltage to the piezo actuator, we could bend the chip. And the result of these measurements is shown at the bottom left. Now, when we apply now, as shown now on top right, this modified plot, if we apply the external voltage, which could be simply a gate electrode located above the chip, either on one side or the other side of the substrate, then this electric field will influence defects on the surface. And remarkably, the difference between the strain dependence on the left and electric field dependence on the right is that some of the defects, they stop changing their frequency. So you see that some defects are not reacting to the electric field. Some do, but some not. And actually, those defects, we believe, are defects in the tunnel barriers. So they're inside the superconductor, so they're sort of covered by superconductor, and therefore they don't really see stationary electric fields applied from outside. And this procedure, basically doing the electric field and strain control, allows us to distinguish between defects on the surface and defects inside the tunnel junction here. So the result of the measurements where we were applying in alternating sweeps, strain and electric field is shown here. So on the horizontal bar above, you see the red regions where we were changing only electric field, and then blue regions where we were changing the strain, and then electric field again, and strain again, and so forth. And then, as you see, some of the defects, they react only on strain, like, for example, this defect, changing the frequency very rapidly, and then staying constant in frequency under the effect of the external field. And some of them actually react more on field than on strain. And by fitting those fragments to a variety of, all the possible hyperbolas, we are able basically to extract some statistics of the dependence of the defects on strain and the field. And by doing that, actually identify the fraction of defects located in the barrier and fraction of defects located on the surface. And the results of this tedious analysis is shown here. So we could have basically information about the strain dependence of the defect properties, as well as the dependence on the electric field. And we also have some statistics of the coherence time, and really can learn quite a lot about location and properties of those defects. Obviously, defects in the junction, they experience the largest amplitude of the alternating electric field during operation of the qubit. So when you excite the qubit from ground state to the excited state, then basically you apply a voltage in a capacitor, which is simply a dielectric of the thickness of the order of 1 to 2 nanometers. And the electric field there is large. Therefore, these defects can be strongly coupled to the alternating electric field, and they would show the strongly coupling strengths in the range up to several tens of megahertz. Now, here is the result of this statistics. So we would see the defects on the surfaces in the order of more than half. Then the defects in the junction we see is only a small fraction of defects. It's about 3%. And typically in the tunnel barrier of the junction, we observe only roughly one defect, less than one defect per gigahertz. However, we discovered that there are many small weakly coupled defects in this circuit, which do not react to the external fields. And this actually reveals the the possibility to fix this circuit by avoiding so-called stray junction. Imagine that you have thin film structure, and then you go from bottom layer to the top layer by forming a Josephson junction. In order to go back to the bottom layer, you need to make another contact between the top electrode and the bottom electrode. And this contact would require then another Josephson junction in the same process, which typically is made of very large area. And usually you make this very large Josephson junction, you forget about its existence. We call it stray junction. However, this junction will also contain defects. And due to the large area, the electric field there will be by area ratio lower than electric field in the quantum junction. But nevertheless, the defects will be coupled to this field and can exchange the energy with the quantum circuit. So in this first experiments, we found that actually the amount of defects in the stray junction was very high, was about 40%, 39%. Of course, this all depends on the technology, depends on the foundry, depends who makes the junction and so forth. So all these studies, they are not really covering all the range of fabrication techniques around the world. But we've been working very close with Google, for example, over the last several years, actually to study the junctions fabricated at our place and also in other places to tell about properties.
No.
Is there a question in the audience? I cannot hear well.
Do you have a pen?
The volume is very low. Can you speak up, please? Excuse me, is there a question in the audience?
No, you go ahead, please.
Okay. All right. So next thing which we were interested actually trying to find at which surfaces these defects occur, because they can occur, for example, at the interface between dielectric substrate and metallic electrode, which is the basically superconductor. They can occur, as I mentioned, on the surface of the qubit electrode in the oxide layer formed naturally on metallic aluminum. And they can occur also on the outer surface of this oxide, which is sort of have on the other side just vacuum. They can occur at a different distance from the edge of the superconducting film along the substrate, where defects will be still experiencing the alternating electric field of the qubit, which of course will decay farther away from the sample. And in order to distinguish between two types, the different types of surfaces, we came up with the idea to apply simultaneously two different DC voltages, one from top of the substrate, the other one from the bottom of the substrate. And in this case, we can make electric field simulation, calculating the field distribution in this kind of generic geometry where we have the edge of the superconducting electrode. This is basically this area here. And then when we apply the electric field from the top electrode, we see the field intensity distribution like shown in color on the left. And when we apply from the bottom electrode, the electric field, we have another distribution which is shown here on the right. And then by comparing the distribution of the electric fields as a function of coordinate, and our system of coordinate we have chosen here, the origin was here at the corner of the superconducting film. And then we go either in direction left or along the curved surface on the right, on top, or go to the right along the substrate. Basically, we have one-to-one correspondence of the ratio of the amplitude change induced by the vertical field, field produced by the top electrode, and the field produced by the bottom electrode. Of course, electric field is always perpendicular to the surface of a superconductor. This actually helps to just neglect the tangential component and then have one-to-one mapping between the field induced by the top and field induced by the bottom electrode. And then by measuring the respective reaction of the defects to these two different fields, we are able to count the number of defects at different surfaces and actually as a function of distance from the surfaces. And the result of this tedious analysis is shown here. So on the picture to the right, you see our system of coordinates. So we have the origin here. And then we have, in red, we have the interface between aluminum, our superconductor, and the substrate, which in this case was sapphire, aluminum 203. Then on the yellow axis goes along the interface between metal and the oxide. And we know that because oxide has specific epsilon, so it's not vacuum, which is another interface between the oxide and the vacuum, which is the green surface there. And then the blue color stands for the defects located on the substrate vacuum interface. And here you see in color associated number of defects in their position, counted to the right or to the left, for different interfaces. So as can be expected, the cleanest interface which we can prepare is the interface between the metal, aluminum, and the substrate, because we could clean the substrate very well before depositing aluminum, and that's where the smallest number of defects occur. Then when we take the surface, the circuit out, then we get the oxide and we get also contamination on the outer surface, we get contamination of the substrate. And here you see the distribution of the defects and actually the number of those defects in the circuit. So we conclude that actually more than half of the defects that reside on the surfaces. We also cannot, of course, tell here, are these plasma damage during circuit fabrication, are these adsorbates? But obviously, the surface needs better cleaning and also needs passivation recipes to avoid the formation of these defects. So this is basically a recommendation which comes out from this study to the technologists really to work on cleaning the interfaces which are exposed to the environment before measuring the circuit in the dilution crest. Now, the last part, maybe last couple of minutes, I want to show one of the more recent developments here. We came up with the idea how one can use actually the control of the defects by electric field to improve the quality of the existing circuits. Suppose that you have some regions where the superconducting qubit is suffering some frequency where it's suffering from the defect. When applying the electric field to, for example, to this red region indicated here by red circle, one can apply external electric field to tune the field away and then find a very nice white spot with the high coherence. That's where the qubit properties is significantly improved. If you need to change the qubit frequency, you'll find again some other frequency at which there will be a defect in the vicinity of the qubit frequency. And then for that frequency, you can find another optimal voltage where the qubit properties will be improved without changing the frequency of the qubit. And this protocol can be applied to different frequencies. One can sort of measure the fingerprint of the qubit, and then applying the external field, one can improve every detail of this fingerprint, improve by applying the field control. And this can be done in reality. For example, if you have a checkerboard arrangement of qubits, like for example, for the realization of the surface code, you would put the flip chip with the electric control electrodes, each for individual qubits, and then for each qubit, you could find optimal DC voltage you need to apply to achieve high coherence at specific frequency. In our study, we have only done it for one qubit, applying the global field, and without going much in detail, you see here that optimized performance is significantly better than not optimized. So we achieved actually the optimization with the electric field, improving the qubit quality in this specific example by about 25 to 30%. So this actually can be applied to the existing chips and doesn't cost much of the overhead because you just need one additional wire to each qubit. Of course, the overhead comes there if you have to measure large circuits, but that remains to be seen how to do it better. So here in particular example, we observe enhancement of T1 by about 23% in average. So with that, I would like to sort of come to my conclusion. I really would be very interested and glad to answer your questions. So I told you some of our recent studies about two-level system defects in superconducting qubits. So they are limiting the qubit coherence. They are the main obstacle now for moving towards scalable fault-tolerant quantum computers, because one needs to achieve the significantly higher quality of superconducting circuits to achieve high coherence. We have developed different techniques, both strain and electric field tuning of frequencies of qubits. By measuring the fingerprints of those TLSs as a function of either strain or electric field, we also can learn about the physical properties. We can distinguish between TLSs and the interfaces. It's of course a tool to improve the qubit fabrication, but also it's a very unique tool to study those defects as the puzzle. What exactly those defects are remains unresolved. Only very recently, people started using the scanning tip devices to detect those defects. There have been very interesting recent work at NPL in UK, where they were able to influence the defects in the resonator by scanning probe. Nevertheless, the physical origin of these defects is still being debated, and further studies here, I believe, will shed light to the physics of superconducting quantum circuits. So thank you for your attention, and I would, as I said already, I would welcome your questions. Please.
Okay, questions? Well, I think of questions in the. Huh?
Okay, I mean, is there some limit on this T1 which one can achieve because of these defects? I mean, is there something which, I mean, like this coherence time, T1, we cannot go beyond, say, 100 microsecond or 150 microsecond or something?
Nowadays, in particular at IBM, they are working with devices which have T1 on the order of millisecond. Could be a fraction of millisecond, could be a bit larger. But as I already mentioned, this T1 is not always kind of a metric because it fluctuates as a function of time. So, but the best devices, they show T1s in the, and actually T2 comparable in the range of a fraction of a millisecond, up to maybe a bit more than a millisecond. More recently, actually, there was a PRL paper from Princeton published actually this spring, showing that one can achieve coherence times over a millisecond by passivating the surface of a superconductor by gold. That's very recent work.
What about different designs like pi qubit? There was a proposal for pi qubits, which can provide probably much longer coherence time.
Well, the proposals for pi qubits, to my knowledge, they largely remain proposals. So there have been attempts to fabricate them or kind of make those devices. But to my knowledge, none of these devices have shown long coherence times as long as conventional ones. There is one type of devices which I believe has a potential to show longer coherence times, is so-called fluxonium qubits. These are flux qubits with very large inductors, which have very low transition frequency between the ground state and excited state. The particular property which one would require to increase to reduce the influence of defects is to reduce the electric fields in the environment. But even transmons made in three-dimensional geometry, which show very diluted field in the environment, they have coherence not exceeding, let's say, a millisecond. With fluxonium devices, people can succeeded already to go a bit higher because significant part of energy is contained in inductive energy, not in the capacitive energy. And therefore, these devices are a bit more robust and also show much larger nonlinearity, which is an advantage.
Okay. Any other question from the audience? Yeah.
So I have a question regarding the strain coefficient. So to control this asymmetry, how you have managed to model or design this strain coefficient gamma, means like how you have control during the experiments?
Well, we came to this experiment empirically. So we decided to basically apply strain, and we did, applying some tens or even hundreds of volts to the piezo actuator. And this turned out to be sufficient to change the frequency in the range which you have seen on the data. So our calculation shows that the bending of the substrate, which means the displacement of the center of the substrate under the strain, is in the range of a micron, which would correspond to the relative change of the atomic distance in the substrate and also on the surface of the substrate, which means in the superconductor, by the relative factor of about 10 to minus 7. So
Okay.
it's a variation, really very tiny. It's like you change the football field by the size smaller than the ball. So the number is basically 10 to minus 7, but we cannot measure it. We can only estimate it and then state that it's actually sufficient to change the frequency of our defects.
Thank you.
Any other question?
Yes, I have one question.
Yeah.
So you said that good qubits they are prone to more TLS, but they are less harmful. I mean, can you please explain what you wanted to mean?
Yeah, if you make better qubits, they will have high coherence, right? So that means that the spectral width of the transition between the ground state and excited state will be very narrow. So basically, your spectral width of the spectral line is the quality of the qubit. However, if you have a defect, even very weakly coupled, it will nevertheless influence a very long coherence time of this qubit. So you will see a lot of weakly coupled defects, which will not destroy the qubit coherence, but which you will clearly observe in the spectrum. So the qubit itself will remain better, but it will detect more defects because you can not only see strongly coupled defects, they are just few, but you also see very weakly coupled defects. It's like you take your optical instrument, a telescope, and you look in the sky. You have a better telescope, more stars you see. So it's very similar here, that farther you go away from the qubit, smaller electric fields you get, more defects you get involved, and more defects you see with a better qubit. That's what I mean. So, but improving the technology, of course, will make better qubits, but it will not mean that you will completely avoid defects, because defects will remain there unless we'll find some magic way of protecting the surfaces and stop defects appearing.
Thanks. Thank you.
Okay, I have a few questions. You have shown the TLS resonances all in the qubit frequency regime, but they also contribute at the low frequency regime, right? So we get a noise spectrum contribution even somewhere in 1 over F noise also.
Yes.
Would you comment on that?
Yes, this very good question. So this is the defects which actually we believe this noise is due to the interaction of coherent defects and incoherent defects. So if you go to 1 over F part of the spectrum, that's where you have these thermal fluctuators, which probably have which appear everywhere, and which also couple to the bars of the coherent ones. And once these fluctuators actually change their frequency, they change the frequency of the coherent defects coupled to the qubit, and then introduce this low frequency noise. So basically the qubit properties is sort of being due to the, the low frequency noise being due to the low frequency fluctuations of the fluctuators being converted in frequency due to the natural stray or elastic coupling to the coherent defects. That's a picture we have at the moment. But of course, there are also other sources of noise, like, for example, these rare events of high energy particles, which generate, processes in supraconducting electrodes due to the cosmic rays or residual radioactivity. There are perhaps other sources of the coherence, but what concerns TLS is this is the primary source which we have in mind.
Okay, so another thing is that you showed the qubit frequency variation with time that went from 20 microsecond to about 60 microsecond within minutes or something like that.
Yeah.
So if you have a quantum computer and your qubits vary, T1 varies so much, what would be the implication of that, of course?
That's exactly the problem, because you need to recalibrate your device, but not all the frequencies of the qubit are so bad. So if you change the frequency, then the qubit fluctuations will also change very significantly in magnitude. And that's what people do when they choose their sort of favorite frequencies for the multi-qubit processor. In my understanding, they sort of find the best frequencies, and then they recalibrate the whole system to make it more optimal in terms of stability. Very recently, IBM came up with very interesting proposal, not actually proposal, they demonstrated experimentally using our technique. They apply slowly varying electric field. And then basically the qubit during the processor during the operation is exposed to different frequencies of the defects coupled to the qubit. And then the coherence time T1 is not large, but it's sort of average between the lowest values and the highest values. So maybe one can use this technique sort of to shorten the calibration. You will degrade the properties of your performance at the best sweet point, so to say, but nevertheless you gain the stability. So that's one of the solutions which probably will be practical as seen nowadays.
Yeah, my next question is, what kind of defects are insensitive to E field? I couldn't catch that point.
The defects which are insensitive to electric fields are defects in the tunnel barrier of a Josephson junction. because if the defect is inside the barrier, it has the superconductors all around, and then the DC field does not influence this defect.
Okay. And what is the stray JJ, stray reception junction?
The stray junction is the very large area Josephson junction, which is typically fabricated during the process of the standard tilted angle evaporation. So you need to make the top electrode of aluminum, and then you need to come to the bottom electrode using the same type process. And then the simplest is to make a very large area junction, which you normally consider superconducting. So this is called stray junction. Nowadays, people actually add additional step in fabrication. They fabricate a bandage to avoid stray junction, which significantly increase the coherence of superconducting qubits.
And I noticed that most of the TLS defects are on the superconductor surfaces, about 60%.
Yeah.
Right. So wouldn't it be better if you have a superconductor which does not form oxide?
Well, that's what people now try to do with tantalum. So tantalum does not form that kind of aggressively. The oxides, of course, there is some oxide form, but it's not that significant as with aluminum or with niobium. So people are trying to search for better superconductors. They're trying also to passivate the surface using different techniques. The problem is that the quality of the junction needs to be high, and the best quality tunnel barrier, which has been found over many years, is aluminum oxide, which is grown on pure aluminum. If you make epitaxial aluminum and grow this oxide on epitaxial aluminum, it gets a little bit better, but not very much, not significantly really to motivate really going to epitaxial growth, which is of course much more complicated. So yeah, so using different superconductors, as you said, or using passivation techniques will probably be a solution, but this is a long process which already is going on for quite some time. And if you look at what happens at EPS March meeting and those sessions where people are studying the coherence, there are many attempts nowadays. And actually, I see our plots being shown many times at EPS last year and this year, illustrating the defects, how bad they are, and everybody wants to get rid of them. But so far, there is no fix for this hack. There is no hack for this problem, which solves all the problems.
So how much do you think the surface roughness of the superconductors matter?
We don't know this well enough. So we know that surface roughness matters for the formation of the aluminum oxide. However, aluminum has a property, even granular form, when it grows, it sort of has very good wetting to the oxide layer which forms. So even granular bumpy layer of aluminum will form a higher quality tunnel barrier. The microscopic of that and surface chemistry of that, it's not fully understood to my knowledge. So there have been a lot of attempts to study aluminum oxide barriers, but I guess at least not to my knowledge, there is no clear understanding what is happening there, how to get things better.
Cobalt disilicide is also a superconductor, and cobalt disilicide does not form oxide. And it also has the 1/F noise, about 2 to 3 orders of magnitude smaller compared to aluminum. So
yeah, I had a quick look. Yeah, I had a quick look at the paper which you sent this morning.
Yeah.
So it's interesting. I have not heard of this material.
Mm-hmm.
Of course, you mentioned that there is a two-dimensional superconductivity in cobalt thin layer, and then cobalt silicide gets more three-dimensional with suppressed TC. Well, it's magnetic, so nobody knows really if one can really make large circuits with that, but that's interesting to look at.
Yeah, but that's an indication that if one makes a Josephson junction with cobalt disilicide, it will probably get rid of all these 60% extra TLS.
Very interesting to check. So think it's a new material, new to me, and sounds interesting.
Yeah. Okay. Thank you. I think there is no more question. Is there any more? No. If there are no more questions, let's thank Professor Alexey Ustinov once again for an excellent talk.
Thanks for your attention and for the invitation to speak at your gathering.
Yeah. We'll keep on discussing things.
All right.
Okay. Okay. Thank you very much.
Thank you.
Yeah.
Bye-bye.
Bye. Yeah. 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 Just about just 10 minutes before this talk started.